Well, good morning once again, good afternoon, good evening, whatever time of day it is for you when you are getting ready to do this very first serious content lecture in our Leadership and Technology course. We're going to be talking in our first module about data communications, and data communications is no longer considered a side act or a nice to have. It is the core of connecting all of your servers, your users, your applications, your data. Everything runs through data communications now. In the last 20 years, the proliferation of data communications networks have changed not only the way business is done, not only the way computing is done, it has literally changed the world, changed the way people live, learn, work, and play. And so we're going to take a look at this in a single module today. There's really no way we can look at this in any serious depth. There are entire courses on data communications that I do recommend that you take if you're interested in this area. But today what we'll do is we'll give ourselves an overview of data communication. So welcome. When you're done watching this, you can go to Blackboard. There are some videos available that you can watch, as well as a link to a pretty reasonable article. There is no shortage of information on the internet, plenty of great wiki pages, lots of things for you to use and read. And I encourage you to dig through all of those as you work on the homework, which is due this Thursday, the very first Thursday of our course. All right, so what is a network? This is a classic definition that includes a lot of different elements, each one in red. I used to give this as an exam question. You see 1, 2, 3, 4, 5, 6, 7 red words here. A network is a collection of systems which are connected via some communication link, and that communication link enables a source system to transmit a message to a destination. The systems, let me get a laser pointer here. Hopefully that'll work okay. The systems are not only the end systems, such as laptops and giant heavyweight servers, they are also the network systems, the switches, the routers, the firewalls, all of those in between systems from the source to the destination. And so when you think of a collection of systems that are in a network, you should think of everything, the systems that make the packets go, but also the transmitters and receivers. They're all considered to be really part of the network. They are obviously connected. And when we look at a communication link, we could be looking at a Wi-Fi link. It could be a wired Ethernet link. It could be a microwave link, a satellite link. Could be any one of a dozen different kinds of, or dozens of different kinds of communication links. It does not have to be a cable. It does not have to be an electromagnetic radio signal. It could be all of those operating in tandem as your message goes from one system to another. These communication links obviously enable your system if you are the user, or perhaps your system if you are the person running the server, to transmit a message. And when we talk about a message, that is a very generic term. It means data. We're going to be sending some bits, ones and zeros, and those ones and zeros are going to be making up some kind of data. It could be a file, it could be a chat message, it could be a text, it could be a phone call, it could be a video, it could be any one of a number of things. But basically, we characterize this as a message. And then we say that message goes to the destination. So networks are, I'm going to get a pen here. Hang on just a second. Networks are naturally represented as a graph. Over here, I have 4 end systems. And what we might do is we might say, okay, let's put a couple of systems here in the middle. There we go. And now this system is going to be connected here to this switch. We'll connect this guy over here to this switch. Maybe there is a router here. A lot of times we would use a plus sign with a router. I'm not putting the switch sign on here. I can't draw that very well. So our switches are maybe connected to a router. There's another router somewhere else. Maybe this is going across a transcontinental link or an intercontinental link. Maybe this one on the top is in England and the one down below is somewhere in Asia. And then this guy connects to another switch. And we'll have both of these systems on the same switch. And so what we see is we see a graph here. This is a link. It's one of those communication links we talk about. We typically represent these links as lines. And so when you're looking at a network diagram, you typically see a line that connects an end system into some sort of a switch. I'll try to draw the switch symbol It's supposed to look kind of like an X there. Pretty bad. You can Google that. Google Cisco switch symbol. I typically use these Cisco symbols because I worked for Cisco for quite a while back in the day. So we have a link up here, and then we have a network system here, and then we have a router here, the router. And so the packet would go maybe from this node here, node number 1, and it would go, I'm going to change colors. Can I do that? Yeah. Here's our path. We're going to go from system 1, we'll go down here, through here, through here. It'll get routed and forwarded, and then it'll end up down here on system 4. All right. And the edges of our network, here comes our laser pointer again. The edges then are called links, and they can be wireless or cables. And don't get hung up on trying to think of a physical representation in these links. They're really a logical representation of a link. And then the intermediate systems are usually switches and routers, but they might also include firewalls and other kinds of communication devices. They might be in a very old network. You might find some repeaters, and you will hear all of these edges or links called things like Ethernet, Wi-Fi, fiber, sat links, short for satellite links. Uh, as I mentioned earlier, some of my early days, we would build networks with microwave links. And so there are all kinds of different links. And you will hear the intermediate systems, like this one right here. You will hear them called switches, and some of them will be called routers. And so both of those perform different kinds of functions. So that's at one level what a network is. But what should leaders be concerned about? If you're a technology leader in an organization and you're not the guy charged with actually tapping the configuration into the switch to make it connect to a laptop somewhere in the building, um, leaders are going to be worried about the overall architecture. They're going to want to make sure that the functions of the network are being achieved, and they're going to hire and trust other people probably to actually make sure those things are being done. So when it comes to a leadership in this technology area, they are going to be thinking about, okay, how do the components, protocols, and applications, how do they fit together? How much am I spending on those things? Are we buying the right things? Are we keeping them up to date? What are the ongoing costs of this network going to be? Is it reliable? Can we deploy our applications on it? And does it provide the performance that we need? These are all things that you would be thinking about. When you look at a network in particular, we just looked at a picture of components, nodes and circuits, but you should also be aware of the fact that there are what we call protocols. And the protocols are the definitions of how these systems talk to each other. As an example of a protocol, I always like to use the example of two people meeting in the hallway in a building, and you may be acquaintances of one another. And there's a protocol there. One person might say good day, and the other person would say good day. That's the protocol. You know what's expected, what you're going to hear, and you know what you're expected to return. Perhaps the next person says, how are you? And then the person who, according to the protocol, heard that gives a reply like, I'm doing great. And they reply, how are you? And so the protocol defines what you're going to say, when you're going to say it, and what the different things mean in the context of when you say it. And our networks are reliant upon these protocols, and it's good for you as a leader to be aware of that. You don't have to understand all the details of every single protocol that operates in your system, and you probably won't. But you do need to be aware that these things are working. Now, every network has to be managed, and managing involves monitoring the systems, making sure they're secure, responding to events, and also making sure that the current security levels are and operating system software levels on the intervening systems are kept up to date. Of course, the network doesn't exist for its own end. The network is a service that you deploy for your organization. And typically you do that so that you can run applications. The applications are what people are using to actually get the work done. And so a lot of times there are network applications that the users may not be aware of. You as a technology leader should be aware that there are internal network applications that keep the network going. For instance, there are things like time distribution. There will be a way to get an official time from an international atomic clock and then distribute that time into your system so that all of your systems can be synchronized on their time. And this is important for security, pardon me, but it's also important for coordination of activities between different devices. There will be name management. For instance, you can go to www.google.com. That's a name, and that has to be translated into an actual what we call IP address. And so we have to manage the names in our organization. And of course, we have to monitor the software. And then there are the end systems. And the end systems are the reason for existence. They're why we have networks. We want to connect these systems and applications together so that we can be more productive. And in fact, it is this connection which has made such a big change. I you think about computers that are made today, it's very difficult to buy a laptop with a CD on it. We would, just as recently as 10 years ago, we would typically want to get a CD player on our laptop so that we could buy software which came on a CD from the store or through the mail, and we'd put that CD on. Of course, nothing like that happens anymore. You buy your software online, you download it, you install it, you update it automatically if you turn that on. And so it's these systems, these software systems, these distributed systems are the reason why we have these networks to begin with. And so as a leader, you should be aware of these different aspects of data communications, the equipment, the management of it, the end applications, as well as the end systems, what kind that you have, what kind they are. Now let's talk briefly about what the physical components on here. This is a very, very low res picture of a high-end router. This is a major league router here. And in the core of the internet, this is the kind of router that you have. If you look at somebody's home, they went down to Best Buy and they may have purchased a router for their home, which they've connected to some sort of cable internet service that they got from Cox, or maybe a fiber service that they got from AT&T. But this is a major, big router. And this is the kind you would see in the core of the internet. And we call these routers nodes. We call the switches nodes. And that comes from the graph terminology that was originally used by the people who invented these first and first started putting them together. This is where all the processing, the network processing, happens at these nodes. It can include end systems because, believe it or not, you may not think of it that way, but the end systems also do network processing. They have to originate the data and they have to receive and terminate the data transmissions. And then we talk about all the links, which we've already mentioned. And these links are often described by the number of bits per second that they can transmit. This is what we call the throughput. For instance, you'll hear the term gigabit Ethernet, which refers to 1 billion bits per second transmitted on an Ethernet link. There is 10 gig Ethernet. You'll hear other phrases which I'm not going to define for you at the moment, like OC192, and these are classic telecommunications phrases which are used in the fiber that connects long haul fiber circuits together. So there are all kinds of different terms. We almost always uniformly apply these, and what we are describing is the number of bits per second, or the bandwidth of the link. The bandwidth refers to the number of bits per second which can be transmitted. And so if you have a what we would call a T1, that's a very slow link these days. That would be 1.544 million bits per second. That would be a T1. And there's some other arcane terminologies as well. Most of the data that you hear described today is more along the lines of Ethernet speeds, gigabit Ethernet, 10 gigabit Ethernet, and if you're operating on a slow computer, you might have what we used to call fast Ethernet, 100 megabits per second. And so the circuits and links are described by the speed that you have. And finally, we have the types of nodes. And really, you just keep these two in mind. We have end systems, and these are the clients of the network, laptops, servers, things like that. And then there are the network systems. The network system is actually a very specific term that is used to describe a computing system which has as its primary and usually only purpose to receive and forward data along the different paths that are in the network. Now, I talked earlier about what's a protocol, and I already gave this example of um, human protocols. For instance, if we were in class together, one protocol is if you have a question that you would raise your hand. And then if I'm being polite and following the protocol, I would call on you. Yes, Bob, what do you want? Do you have a question? And then Bob would say, yes, could you go back to the previous slide? And then we actually have a protocol for that. And the protocol tells us how we're going to behave. Well, network protocols do the same thing. They define two very important things. They define the way the data is going to be organized in each packet of data that's sent. And there are usually two parts. There's a part of the packet that is there to get the data delivered. It has the address and information about the packet, how many hops it's been through, how big the packet is, what the packet's priority is. And this is information about the packet itself. And then we actually have the data that's in the packet. And this is oftentimes what we refer to as the payload. If you were driving a truck from Boise to Minneapolis, and you're not getting paid to drive the truck, you're actually getting paid to deliver whatever's in the back of the truck. And that is the thing you're paid for, the payload. And so the payload on a data packet is the actual user data that's being transmitted. That is why the packet was created. In addition to defining the packet format, a protocol also defines the states. And by states, we simply are referring to a state machine. Are we just beginning our conversation? Are we in the middle of our conversation? What if we want to terminate our conversation? Those are all different states that the conversation or the connection between the two end systems can be in. And so all of the different systems from the transmitter to the receiver all participate in this protocol. They all know how to understand the packet format, and they all know how to take actions based on what's in the packet and what state we're in. All right, so we're looking at what is a packet. Sorry, I had to re-record this slide because I got into a bit of a coughing fit there. Got something dry in my throat. What is a packet? A data structure with a header and a portion. We already talked about that. And the header usually contains the meta information about the data. Where's it going from? Where's it going to? What's its priority? How much data is there? That is the portion of the packet that describes how to deliver it. All the network systems will use that information to forward the packet and deliver it appropriately. Then there's actually the payload, and that's the data that the user wants to get delivered. If you were driving a truck from Boise to Minneapolis, and you were getting paid to do that, you're not getting paid to drive the truck. You're getting paid to deliver what's in the back of the truck. And so the load in the back of the truck is what is being paid for, and we call that the payload. And that really just refers to the user data. So data is sent via packets. And sometimes you may hear people refer to them as frames or datagrams, but they all refer to this idea of organized data that has a header with information about the data and a payload, which is the actual data that we want to send. And now we're talking about another term called topologies. And topologies is a mathematical term, and it refers to the way in which the network is arranged or connected. And there are many different kinds of topologies, and one of the important things for you to keep in mind, particularly as a leader, is sometimes people will be showing you diagrams of an actual physical topology. They're going to be looking at the actual cabling that's happening in a building, or the paths of fiber optic circuits that run across a campus or maybe run from one city to another. And so we have physical topologies, and this refers to often how things are equipped. But there are also logical topologies. You will oftentimes see someone, I'll get a pen here and do this real quick. Let's see here, see if I can grab a pen. There we go. That you will have someone say, I've got my, here's an IP phone, I'm going to use it. I've got my IP phone and it's connected to, and they draw a cloud and they put a big I right there and they say that's connected to the internet. And then this cloud is connected to this switch, which is connected to that other switch, which comes all the way over here and is connected to, that was cute, and is connected to this phone. But this is a logical diagram. It doesn't show us all the interconnected points and all the interconnected devices. It's at a higher level and it's abstract. And so you're going to see a lot of logical topologies as well. Now, there are different kinds of networks, and a lot of these are historical, and some of these have kind of merged with each other over time, but it's important for you to at least have a little bit of understanding of some of these terms. So we'll cover them here real quickly. We have what's called a LAN and a WAN. Those were the two most basic and most common terms that people would refer to. A LAN stands for a local area network. And if you were operating a LAN, that typically was in the you could have a LAN in a room. This is kind of the area that you would see a LAN. And most often when people describe them, then you can see right there, local area network in my little diagram. most times when people talked about a local area network, they were talking about something with geographic proximity to each other. This would typically be things that were very, very high performance because you could do higher transmission rates across local cables. That's not so much true today. We have some very, very high transmission rate, long haul cables, fiber optic cables, and systems that are in place now. So we don't have to worry about those as much. And then the WAN was the wide area network, and you can see that right here. And this is typically between cities, 60 miles, 100 miles, maybe between continents, 600, 800, 1200 miles between two different locations. And this was the wide area network. And then we had the metropolitan area network. And as its name implies, this would be a network that would go from one part of a city to another, usually built with fiber. And how can you tell them apart? Usually the number one thing was geography. Used to be speed was a big differentiator, but not so much anymore. And then the different kinds of networks have different physical protocols and different physical media. Usually you will, for these you see wireless connections in a WAN, and I don't think you're going to see that quite as often in a, I'm sorry, wireless connection in a LAN. You're not going to see it as often in a WAN except for satellite links perhaps. And then you typically see fiber optic connections for long haul, anything that's going between one building and another, or certainly from one city to another. And in these networks, sometimes they are broadcast networks, which means a packet that goes onto that network goes to every destination. Sometimes they're point-to-point networks. Now, we also have this idea of connection versus connectionless, and this is a little bit esoteric, so I'm not going to get into it too much, but basically, this describes the difference between two types of communications. Imagine that you are going to turn on the radio and listen to the radio. In order to turn the radio on, you tune it to a station and you receive the broadcast of the station. Now, the station that's broadcasting the music or the news or whatever it is they're broadcasting on the radio, they have no idea if you're connected, and you don't have to let them know that you're going to connect. You just simply tune in and listen. That's a connectionless network. Now, you could argue, hey, there's a connection in place, but the reason we call it connectionless is because there was no prior arrangement made between you and the sender to agree that the sender will send data to you. The sender is sending it out and just hoping that people will listen. The reverse of that is what we call a connection-oriented link. And this is a link where the two ends must negotiate and agree to certain parameters. And once they do that, then they have established a connection on purpose with information that's been exchanged. And so each end is aware of that connection. And usually when the communication is over, they tear it down. They disable it, and so it's no longer there, because a connection-oriented link has resources on both sides, memory and processing and things like that are allocated to that link. And once they're done, you want to let them go. All right, we have two communication models, and you will have heard of both of these, I'm sure. These communication models involve the end systems and how they work with each other. The first is a client-server model, and this is very much like there is a server somewhere. A web server is a classic example, and lots of clients. The clients submit requests to the server answers those requests, serves them, sends the answer back. And now a client-server model can happen at the physical layer. Your system, your local laptop may be connected to a Wi-Fi access point, and so you have a client. You're a client of the access point, and that's happening all at layer one. Or you may be a client of an email system. That is also a client-server system. The other type is a peer-to-peer model, and this is a situation where all of the different devices are peers of each other. There's not any one that's in control. And an example of this is a Skype or a BitTorrent. Now, this was a BitTorrent was a way in which files could be transmitted from a number of sources to a single destination. I encourage you to spend a little time looking at BitTorrent if you want to learn more about that. But peer-to-peer models are basically every system can talk to every other system. They can all communicate and send data directly to each other, and there's not one that is particularly in control. Now, when you compare these two, the client server has one device making requests from another. The client is usually not in control. They have to request service. Clients don't actually communicate with each other directly. They go through the server. And so an example would be I have here a student teacher. So if everyone's in the class, the students usually ask the teacher's question. The teacher usually responds to the students. That's a little bit of a client um, server model, or a printer. Everybody uses the printer. You send your data to the printer and it prints it. You don't send your data to somebody else's laptop uh, to have it printed. You talk directly to the server. In a peer-to-peer node, all of the different systems talk to each other. And you could imagine a system, maybe there's a video game and 12 people in the same room are participating in the video game, and each computer that's running the video game sends data to whatever other computer needs to have it. There's no one game server. Everybody just is a peer of each other, and they're all sharing data uh, in a point-to-point fashion. It's also possible to have hybrids where there is a central server that tells systems how to connect to each other. And voice over IP, some voice over IP configurations can work this way. You want to make a phone call on your voice over IP, you actually ask the server to connect you to some other end system, and that server contacts that end system and says, would you mind talking to this person? And if the person accepts the call, the server then connects you directly to the other end system, and now you're doing peer-to-peer, and the server steps out of the communication. That's a hybrid solution. So we have all three, but really the two to be aware of are client server and peer-to-peer architectures. Again, back to what would a leader, a technology leader, be concerned about? You're going to be concerned about security. You're going to want to make sure that that you and the staff that you're working with are putting security policies in place, that the data is secure. You're going to be needing to think about scalability. One of the things that just seems to always happen in data communications networks is the network demand just never stops growing. And so you want to have architectures and designs that grow or scale up as the demands grow. You definitely want to have reliability. Every network system, people who use it are going to be counting on it. You're going to have mission critical, business critical applications. Your organizations are going to um, have to have it. I tell you, there's nothing more debilitating nowadays than when the network in my building goes down. I really can't do much of anything at that point because I rely on it for just about everything that I do. You're also going to want to make sure that your organization is compliant with civil standards. And by this, I actually mean laws and ethical obligations. That we have the European model here, which is referring to the privacy of data that users have. That's the GDPR rules. And in America, we have the HIPAA rule set. You're going to make sure that you, as a leader, that your organization is complying with these rule sets so that you and the other people who are providing the data communications do not create problems or get in ethical problems or even legal problems for yourself. And finally, you're going to be concerned about management. And the management of the network, here we're talking about monitoring, automation, managing the growth, managing the problems, things like that. So these are things that you should be thinking about, that you should be aware of, and make sure that you are having these conversations with your teams. Let's talk about a couple of these in a little more detail, and then I think we'll be done with the lecture for today, and you can go on and look at a couple more videos and get the homework done, hopefully on time by 11:59 p.m. on Thursday. All right. When we talk about network security, what we're actually talking about here is confidentiality. We want to make sure that the transmissions we send are protected. And one of the ways we do that is through encryption. In fact, most connections nowadays are encrypted. It's almost rare to have a connection that's not encrypted. Um, but there's more to it than just ensuring confidentiality. There's also availability. Security is usually when people think about it, they think of, oh, their fences keep the bad guys out, and that certainly is a major part of it. But another major part of it is, are the systems going to be available? Are they going to be up? If one part of the network dies, do we have an alternate route that we can use so that we can guarantee service to our users, or guarantee as much service as possible to our users? And a lot of times you will hear someone refer to 5 nines or 6 nines. And when you hear that, you just need to know that, for instance, 5 nines of availability means that the network is available 99.999% of the time. And 6 nines is an extra 9 on there. 99.9999% of the times is 6 nines. And you want your organizations to build the networks and manage them and monitor them in such a way that you provide these high levels of uptime service. Notice that this uptime uh, calculation doesn't mean that every device is up all the time at that level. What it means is that the network service as a whole is available during that whole thing. Of course, you want to protect your network against threats like hackers and different kinds of malware that could be deposited on end systems or in the intervening nodes. And you want to make sure that you and your team are identifying exposures and mitigating them. And this typically involves firewalls, what we call IDS, intrusion detection systems. And I'll just quickly comment here. We have two kinds of IDS systems. There's a HIDS and an N as in Nancy IDS. The HIDS stands for host IDS, and that's something that you put on an end system, maybe like a virus checker or something like that, and it detects intrusion on the host. Then there's a network IDS, and these are oftentimes appliances that you put on your network that monitor network traffic, either in a pass-through or in a passive mode, and they watch the traffic and look for and try to detect patterns uh, uh, and specific packets that might be sent that are considered dangerous threats. And so those are important parts of your network to ensure that you are not vulnerable to stuff. Of course, virus detection systems are part of the host IDS that I just mentioned. Finally, you're going to want to have some mobile security policies in place. And this is a big part of being a leader of a technical organization or leader within a technical organization, is recognizing that mobile systems provide a unique challenge for you. And what you want to have in place are some policies that protect organizational data from damage or exposure. You're going to have users who have organizational data maybe on their phones, and there are multiple different ways to address this. You need to be aware of those and be ready to make sure that your organization is taking advantage of the different tools that are out there. Some other policies you might want to have. Do you want to have a remote wipe policy? In other words, do you want to have the ability to remotely wipe one of your users' phones if you sense, for instance, maybe the user says, "Hey, I lost my phone on the train." Do you want to be able to go out and remotely wipe all the data off of that? Now, your users may not like that very much, but if they're going to put the business's data or the organization's data on there, may be a requirement. Maybe you'll have a canister policy. This is the way Cisco handled it when I worked for them a couple of years ago, that they would have what they actually put what was considered a protected canister environment. And so when I was going to use Cisco data or connect to Cisco systems, internal networks, I would have to open the canister and I would operate from within that context on my phone. And Cisco could remotely wipe that part of my phone without wiping my entire phone, which I thought that was a very, very nice thing. Finally, another big part of that network security is disaster recovery. What are you going to do if you get hit by a big malware attack? Or what are you going to do if a tornado hits your business office? And so you need to be thinking about what kind of plans you're going to put in place to recover from a breach or a physical disaster. We talked about scalability a moment ago, and this really is a very simple question. How well does your network grow as the demand grows? And depending on how you design it, it will either scale up well or it will not scale up well. And so you want to make sure and be asking those questions. Are we going to be able to grow? What's the next step? What will it cost to grow to the next step? Will we be able to continue using our existing equipment and add it in a linear fashion, or is it going to become exponentially more complex because of the way we've built it and the protocols that we've used? Typically, you want to have hierarchical network topologies, and that involves sort of building a core with a distribution layer and then an access layer. And the internet is built on that kind of an architecture, and we can see how well it has scaled into a worldwide endeavor. And the last thing I have on here is a special note about corporate data centers. They're kind of a different animal. There are so many servers, so many computers. They must often be connected point to point. And the way that we build them is just a little bit different. That would actually be an entire 2 or 3 or maybe even semester-long course all in itself. But just be aware that corporate data centers have a little bit different architecture, and if you begin to build out or are part of building out a major corporate data center, I'm sure you'll be looking into that. But we're not going to be able to go into that today. I just want to make sure that you know, though, that there are different architectures for the data centers. Then we talk about reliability, and there are a number of different ways that you can achieve this. We usually have hardware redundancy as well as software redundancy. We try to put fault tolerant systems in place. For instance, we want to make sure we have multiple power supplies in our network systems and servers. We want to have RAID systems on our disk drives. We probably want to have multiple processors on both our network systems and our servers. And so we're tolerant. If a piece of that falls apart, we have a backup that's already built in that we can use. Sometimes people develop load balancing networks, and so that there are two different paths from point A to point B, and the data is sent on both paths, so that there's load balancing. If you want an analogy, really, there's nothing more simple than just thinking about there are two lanes on a highway, or going to a third lane on a highway. The more lanes you put on a highway, the more paths there are for people to drive their automobiles, and people can balance those lanes out. It's always kind of a funny point to me that you pull up to a light here in Edmond, Oklahoma, where I live, and people don't load balance. There'll be 15 cars in the right lane and 2 cars in the left lane. And since I like load balancing, I'll go ahead and do my part and get in the left lane, which has a shorter line. Quality of service is another topic that's a big one, and it'll be up to you to help guide your organization and ask those questions about what kind of quality of service do you want to provide? Do you want to prioritize video traffic, for instance, or do you want to prioritize certain kinds of video traffic? Maybe, for instance, at Oklahoma Christian University, in the past, I know that they actually reduced the priority for video traffic because so many people were watching movies and stuff in the dorms that it was actually getting in the way of actual school business data that was trying to be transmitted and received. And they did that by assigning low qualities of service to the video feeds that people were watching when they were watching Terminator movies and Gilmore Girls or whatever else that they were watching. And of course, you're going to have monitoring policies. And this is going to be situations, simply you setting up the ability to be monitoring the different devices and making sure that they are up and running and that you're notified if there's a problem. Finally, we have this idea of compliance. Maybe this isn't the last slide. I think we have one more after this. And when we talk about compliance, what we're really talking about is being aware of these civil and international privacy and data protection regulations. And since you, in your data communications network, are actually going to be carrying this data, you are also going to be held accountable for making sure that it is secured, that it is treated with the privacy that it needs. A lot of times you may need to do training for those employees who support the network so that they understand their obligations and expectations around this sensitive data. Could be personal data of users, could be health data, it could be any one of a number of different kinds of data that is considered secure. You should put into place regular audits, self audits, external audits that conduct and assess your privacy practices to make sure that you are complying with international and national laws and regulations. If you're a big enough organization, you may actually have a data protection officer, somebody who watches these organizations, making sure that you're keeping up with new laws and new addendums, but also is, guiding the organization and training employees and putting training in place and things like that. Regardless of whether or not you have a DPO, you or someone in your organization has to stay current with these changes and developing best practices so that you can change when the laws change. In the last 20 years or even 10, we've had significant changes in protection for people who use communication systems. And that's only going to grow as more and more people are exposed and there's more and more concern for privacy. Then those demands on organizations that provide and use data communications are going to get heavier, and it's going to be incumbent upon organizations and leaders to be aware of those rules. Finally, I have here network operations, and there is a question on the homework for you to do a little digging on this. You will see the acronym SIEM, and this stands for Security, Information, and Event Management. And this really refers broadly to the idea of monitoring your network, making sure that the information is secure, but more than that, having processes in place for when there's an outage. How do you respond to it? How do you escalate? Uh, Processes in place for when there is a security breach. Again, How do you respond to it? When will you engage external authorities like the FBI or somebody like that? SCIM policies integrate your firewalls, your intrusion detection systems, those IDSs I referred to earlier, routers, switches. They refer to keeping your software up to date. They have escalation policies. They even have policies for how you're going to forensically go in and investigate events after they happen. Usually, if you have an SIEM policy, sorry, you will have systems that are set aside strictly to log the events and monitor data that's going through your system so that you can go back, if there's been an event, you can go back and look at what was happening in your network. And finally, there are going to be policies put in place for response handling, escalation, reporting, post-event analysis, all that kind of stuff. So you're going to be asked in the homework to do a little bit of digging on this. You're not asked to get real deep. Just write me a couple paragraphs, and you may even want to just focus on one of these bullets here in your response to that. You're asked to go do a little bit more digging about that, learn just a little bit more, and then report back to me about what you find. All right, so now it's your turn. Homework number one is available on Blackboard. Now, I do have a note here. I hope that you have made it to this part of the lecture so that you are going to hear this note. Be aware that the homework assignment is in one file on Blackboard under Module 1, and you have to then submit your response. Your Word file or your PDF file must be submitted through the Turnitin assignment. The new Turnitin doesn't let me put the assignment file inside the same link as the Turnitin. So download the assignment, read the questions, build and write your own response, and then submit that through Turnitin. Good luck to you. Thanks for listening. This has been about a 40-minute lecture, and probably going to be typical for some of the lectures we have this semester. I think others may be a little shorter going forward. And good luck to you. Please email me if you have questions, and I look forward to seeing those homeworks submitted by 11:59 p.m. And don't forget, if you can submit them 48 hours early, you're going to start piling up some bonus points, and those can make a big difference in your grade over the course of the semester. Thanks a lot. Have a great day, and I'll look forward to hearing from you if you have questions.